Yeah, got it.
Yeah, it's great. We're live. We're on YouTube right now.
Excellent. Hello, everyone that might be watching on YouTube. And Hugo, can you keep an eye on YouTube in case someone's there and wants to ask me a question?
Sure, I will.
All right. And we will go to this window. You guys should have access to this notebook, but if you don't, I'm going to put the link to it. It's a view-only link, so you can make a copy of it. And I'm putting it in our chat, just in case there's someone new here that hasn't had it yet. Now, guys, I got sick, and the time I normally had set aside for preparing for this got chopped. Let's put it that way. And I've also been studying geometric algebra because I wanted to be able to explain how to do cross products in more than 3 dimensions. But what I thought we could do to augment today, which is a really great fallback, is I'm going to go ahead and show certain screens on Saul's lectures, and we'll talk through the math that derives these 2 properties down here, which some people have been very eager for me to point out. So you may have seen the cross product done by other means, but this is a means that I can't remember, as I said in my LinkedIn post, if you saw it on this. Did I come up with this myself? Did I learn it from my physics professor, from my physics textbook? I can't remember anymore. It's just when I have to do cross products, I use this. But I want to show you something. Cross products are necessarily 3-dimensional. And you might be thinking, whoa, Tom, you mean you can only do these in 3 dimensions? Yep. Can you only do them with 3-dimensional vectors? No, but if you have 2-dimensional vectors, you need to extend those 2-dimensional vectors to 3-dimensional vectors by putting a 0 where that 3rd dimension that they didn't include would be. So let's say, for example, here I'm showing x cross y, and they're both vectors, and they have components of x1, x2, and x3, and y2, y1, y2, and y3. And you know, I've probably confused this. And why am I saying that? Because normally we reserve x and y for the direction along the x-axis, and y for the direction along the y-axis. And actually, Saul uses A and B. But I kind of want to ask y'all to do something different in your minds. Along the x-axis, we're going to think of that as the I hat direction. And that's what I've done here with this I hat. That's to remind us that these are unit vectors, and they're reminding us of the directionality of these components for each of the vectors. So they're along the I hat vector, which is a unit vector, so that when we use this in a multiplication, it won't mess up our stuff. So we use that to show it's the result of this product of these 2 elements of x3 and y2. They're basically in that I hat direction, or as we classically say, the x direction. So that's the 1st dimension, the 2nd dimension, the 3rd dimension with j hat and k hat. So I hope you'll just keep that in your mind's eye, in your memory as we go through this. And so if x and y were only 2-dimensional, we would put in 0 for x3 and y3, but those would be along the k hat direction, or in the z direction. And the way this technique works, and Saul shows another way, and I hope you're watching all his videos. I need to add those video links in our notebook. So also, if you want to see ahead of time where we're going with what I've done for Saul's lectures, then all you'd have to do is open this notebook, or you can even send me a message on LinkedIn or in our Slack work group to say, hey, have you updated the workbook yet? When do you plan to do it? And I should say notebook. This is a Google Colab notebook. And you can run all of this once you've downloaded it and saved it. You can run it as a Jupyter notebook as people pronounce it, but it's spelled Jupyter. And but here I'm just showing the Latex Math. And let me show you how this technique works. First, you just lay out X and Y vertically with their components. And again, if one of the components is missing, it didn't have a value, you just put a 0 in for that position and you'll be fine. Then to get this first value here, we only do, yes. Oh, someone went off mute accidentally. Let me see if I can find out. Oh. I don't know who. Oh, wait, here we go. Nelson, buddy, could you go on mute unless you have a question? It'll help our sound. Thanks, Nelson. We all do that sometimes. No problem. Thanks for doing that. So this is purely diagonals. We don't wrap around. But what I did was I wrote these vertically. Then I wrote, according to rows, X1 and Y1 are both along the I hat direction. And X2 and Y2 are along, oh, no worries, Nelson. We just help each other that way. Sometimes it happens. Now, X2 and Y2 are in the J hat direction. And X3 and Y3 are in the K hat direction. So now we just repeat X1 and Y1 over here. But we're just going to go purely diagonally down. We go X1, Y2, K hat to get this value. And when we're going down, they're positive values. Or we put not positive values, we put a plus sign here. And then Y1, J hat, X3, and then I change the order. So it's always X's then Y's. And then I hat, X2 and Y3, change the order to keep things straight. And then now I go upwards. So I've got X3, Y2, I hat, and then minus whatever that comes out to be. So here, whatever this product comes out to be, oops, I'm just going to keep the sign. But whatever this product comes out to be, I'm going to negate it. And the I hat, J hat, and K hat, as a matter of convention across all of physics and math, we keep those positive. They're just unit directions along their respective axes. So the same thing, but now as we come up vertically, we are just saying we're going to negate whatever product we got, and then this one. And then we take all of these quantities that are down here and up here, and we group them by like unit vectors. So here are the two I hat ones. So we go this one minus that one. And then we go this one minus this one. And then we go this one minus this one. And that's all that's occurring down here. So, hey, we could write the Python code for this, and we'll do that later. Now, some people in the past were really eager for us to get to this very point right here. Oh, and I've already made, this will be fun. Let me see if I can get right there. I have made an error in this equation right here. Can anyone possibly tell me what it is? I'll give you all a second to answer. Hugo, could you hum the Jeopardy theme song for me while we're waiting? I'll do it. Do, do,
All right.
do, 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 do. Oh, that's long enough. So when I do it this way, over here on the right, this is going to give me a scalar value. But cross products, as you can see, give us vectors. Okay, that's very significant. So what should I have done? I should have said, it's the magnitude of the cross product. But, oh, wait a minute. A vector is magnitude and direction. So what you're telling me, Tom, is if I do this operation on the right, I'm going to lose direction information. And that's exactly correct. But, okay, Tom, this operation, this cross product operation, I see that you've retained direction information because you've got components in the I hat, J hat, and K hat directions. That's right. In fact, what are we doing with these operations? We're just finding a scalar multiple on the unit vector in the x direction. That's what I hat means. If we wrote it out as a 3D, it would be 1, 0, 0. And J hat would be 0, 1, 0. And K hat would be 0, 0, 1. So we're doing scalar multiples on each of these unit directional vectors. And so that way we know the components, we still know the direction. But when we go to this level of operation, we lose that directionality information. Now, you might ask, relative to x1 and y, excuse me, relative to vectors x and y, well, let's do this. Let's say that this is going to be a new vector that we'll call it, I'm just going to call it A, so we don't overuse Z. And so you can see right here, what can we say about A with respect to X cross Y? Well, this is interesting. Do I have multiple points on the plane? It's interesting. I just have 2 points here because these vectors, I can say they've traveled from some origin to some point in 3D space. And this is what I'm missing here, guys, because I got sick. But I'll catch up with some more visualizations. But picture X1 and Y1 are lying on some plane, but that's just 2 points. And you say, oh, wait, Tom, no, that's more than 2 points. That's, 2 vectors. You've got, no, but still, this vector's defining a point in 3D space, and this one's defining 1 point in 3D space. And what do I need to define a plane in 3D space? Can anyone tell me? There's 2 things, there's 2 ways to define a plane in 3D space. Tell me both of them if you can, and you can put it in the chat or come off mute. Do, 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 do. Okay, long enough. So you need either 3 points, and that would give us 3 points because the plane can't, it's like the stool example. The stool can stay upright as long as it has at least 3 legs, but it can also, we can put a string right at its center of mass. It has no legs, and now we put a rope up above it and we hang it. And now it becomes a swing seat. Maybe we tied it to a tree limb. And now that plane in 3D space, that little seat that we can sit on, it's got a normal vector going out the seat. Well, this is what's cool. If we only had 2 points in 3D space, and they were defined by 2 vectors, so yeah, we know the direction from the origin to the point on the plane, but I still need a 3rd point, or I need a normal vector. Well, let's realize A is not X and A is not Y. It's X cross Y. Well, this uniquely defines a normal vector to the plane defined by this cross product. So what we're doing is we're sweeping from X. Let me watch my hand here. We're sweeping, and I should do it. I got to do it with my right hand, so let me do it this way. We're sweeping from X to Y. Well, if we use the right hand rule, that means that new vector A is pointing straight up. But how is it pointing straight up? It's pointing straight up such that it is perfectly perpendicular to that swept plane. So here I went from X to Y. Well, that sweeping action, and that's what the cross product does, it formed an area as it swept the shortest distance from X to Y from the points, but they're points along that plane that they're lying in. And the normal vector to those 2 vectors is A. Now, you might be realizing, oh, wait a minute. In your case, the 3rd point was 0. Yes, it was. That would have been the 3rd point. But we can also get there to that normal vector this way. So if you're ever wondering, well, shoot, if I have 3 points, but now I make 2 of those, and one of those points is on the origin. Now, if I sweep across, those 2 vectors, that's how you get this normal vector. So this is a little limited compared to what we looked at when we did these, the equation for a plane in 3D space. And remember, all these principles we learned above, they extend beyond 2 and 3D spaces. But the cross product's a little strange in that way. We can use dot product on thousands of dimensions, but this method I showed for the cross product is only 3 dimensions. And this technique cannot apply to a 4th and a 5th, or excuse me, real numbers in 4-dimensional space, 5-dimensional space, etc. Well, how do you get the cross product for beyond 3D space? That's why I'm studying geometric algebra. And I'm really hating that I didn't have someone encourage me that was my age now, encouraging me when I was your age to study geometric algebra. But at the same time, it's probably easier to learn now because of the 2 really good YouTube channels I've shared on LinkedIn. But still, back to this. Now let's get some insight on this. Remember, the magnitude of this cross product is going to follow the magnitude of X times the magnitude of Y times sine theta. Well, where is theta at a maximum? Come on, someone. It's okay if none of you know, but I hope some of you know. We might need to go over some basic trig 1 lecture if y'all want. You can let me know. Well, sine theta, if you remember your sine wave on an XY graph where X is theta, and we should say theta and Y graph. If we take the sine of an angle, when it's at 0 degrees, it's at 0. But then it goes up quickly as you raise the angle. And then when it gets to 90 degrees or it gets to pi over 2, that's where sine of theta is a maximum. And then as you go beyond 90 degrees, it starts going back down until it gets to 180 degrees, and then it's 0. Now, as it goes beyond 180 degrees, it goes negative. And as it gets to 270 degrees, or 3 pi over 2, that's when it's minimum, meaning the largest negative number. And then when it comes all the way back around to 2 pi, or 360 degrees, that's the same as 0 degrees, and sine theta is 0 again. So what that tells us, oh, this is like the area of a parallelogram. Interesting. That means A, this normal vector to x cross y is going to have a magnitude that's equal to the area of a parallelogram. And again, normally I would have drawn this stuff out for you and reminded you of the trig principles, but like I said, I lost hold of my prep time. Now, and please, I beg y'all, take the extra time to watch Saul's lectures, at least up to the point where we are. Then you can go back through these new notebooks and back through our recordings and see more. Now, the dot product's a whole different animal. It always gives us a scalar value. There's, you notice I don't even have to put the how do I put that? So this is the Euclidean norm. Oh, Emmanuel. So let me take you through this notebook real quick. If you go up here, if you go through this notebook, I embed links to all of Saul's lectures that we've covered. And so each of these major sections will have video links. And yes, I still need, that's just a compact review, but then I still need to add the video links to where we are. See, I think those, so yeah, here we go. Vector dot, oh, they're already here. We're still in this section. So I probably should, I will indent all of these. So these are the lectures we're in right now. And today we're going to go through, we've been going through this one, cross product introduction. Then I'm going to show y'all some stuff here. And then we'll get to this next time. So, yeah, these need to be indented in some. So we're here right now. And I can do that real quick so y'all know how to do that yourselves. We'll just go ahead and, learning Markdown is a great skill. So that brings me in one level over here on the outline, as you'll see. And then I'll go up to this next one. And yeah, I made a big deal about centering that too. And I guess I can leave that. That's all right. It's still going to show up right in the outline. So yeah, all of this stuff follows under vector dot and cross products. And these two products are so important. That's why we want to make sure we really not just know the equations, but we gain some intuition for them too. Okay, so now all these make sense from a table of contents point of view. So now that if I go back here, you see all of these fall under vector dot and cross products. And again, Emmanuel, oh yeah, you bet. I just saw your reply in the chat. All the lectures we're working through right now are here. So what I still owe you guys, or even better, you could say, Tom, we got it. You go through the next two videos from where he covers cross product introduction, and you lay out the LaTeX for the proof of what we're going to look at on his videos here in just a second. and you code this up in Python so that someone can send you two vectors, and you can even check to say, hey, I need a 3D. I know you may have only had two 2Ds, but you know what? The result's going to be in that third direction because it's going to be normal. So I need a three-dimensional vector. You can put the assert statements or the logical statements to make sure that when someone sends in two vectors to your code, it can have all the information it needs to give a legitimate cross product. And then, yeah, you'll put it in components, but you can also say that the magnitude of this cross product, and oh, you guys might have been thinking what I just realized here. Let's cheat and go copy and paste. Obviously, I think some cheating like that. It's not really cheating, of course, but why retype it when it's faster to copy and paste it? Okay. This new A vector, again, I'm beating it to death. I hope y'all don't mind. It has magnitude and direction, but its magnitude is equal to this right down here. All right. Let's go through Saul's excellent lectures on, you know what, we'll go through each of these. I'll just go to the last screen. We'll show you how it matches. So there's a trick here. I won't be sharing his audio. I don't know if y'all could have heard that last little bit. And now this may look messy, but you kind of have to watch it to realize, oh, I understand the mess. So let's go back a little here. And there you go, A and B. And he does A cross B, and it comes out just the way we said, but you'll see that Saul walks you through another method, and it's a beautiful, simple method. There's nothing wrong with it. But, well, Tom, why do you use your method? Because I'm not as smart as Saul. I can't keep that in my head. I have to do it the way I just showed you. But let's look. For each of these, for each of the components, well, if you're looking for the I hat, it's like you cross out this row and you're just doing these two. And then when you're doing it for the new direction for A in the second component direction, the J hat, you cross out these two, the very ones that, you know, are in along the direction you care about, and you cross these two, but you do it with opposite signs. And then finally, you cross out this row to get the new version for this row on A, or excuse me, the result. And you end up crossing these two. And you do it with this sign order over here. But I just find that other way I showed y'all is easier. Yeah, I could keep track of this. I was half joking, but it's just, if I were in a test, by the way, I developed a lot of methods. So if I was nervous in a test, it was brain dead simple for me to get the right answer. And I found that the extra time it took me to write this out on paper was well worth it to do it this way. But if you compare, you know, you can download this notebook and then make a copy of it, and then now it's yours. You could go in here and say, well, no, this is C now, and I'm going to name X, A, and B like Saul's lectures. And so these would be A1, A2, A3, B1, B2, B3. You could make all this like his, and just, you'll prove to yourself that, oh yeah, Tom's method does the same thing that Saul's showing. Okay, you go, I got your message, just so you know, no problems. Okay, and then he does it with actual numbers, just to show you the mechanics of it, and that's great. But then he's giving you the intuition. Here's A in space, and here's B in space, and if I sweep it across like that, that's what that cross product's doing. It's actually making a parallelogram. We'll see the proof of that in a minute. A cross B is actually perpendicular to the plane that's formed when you move up. Basically, to make it a parallelogram, we take a copy of A hat, or vector A, and slide its tail up to the tip of vector B. And then we make a copy of B, vector B, and we slide the tail of that new vector over to the head of vector A, and it forms that nice parallelogram here. Well, that's an area, and this A cross B, we can move its tail anywhere we want. It's always going to be normal or perpendicular to this AB plane that we created by putting a second copy of each of these vectors and forming that parallelogram. So then he goes a little further and he shows the right-hand rule. So all that is now he's doing it this way, where your index finger is A and your middle finger is B, and then it shows what direction the new vector, the cross product, is going to form. I learned the right-hand rule. Go from this way to this way. It's fine either way. I actually do kind of like this one sometimes, depending on what I'm doing. And sometimes I prefer this one. But it's the right-hand rule. This will not work on your left hand, because if A, B, and the vector's down, nope, that's going to give you the wrong sign. It is the right-hand rule. It's so comical to me. If you want to really mess with someone, especially one of your teachers you like to joke around with, they're teaching you to say, so like this, right? And they'll go, no, no. Or you might even fool them, say, Professor, I was using my left hand. But geek jokes, they're the best, aren't they? Okay, now he shows a really neat thing. We're sliding over that screen we were looking at. Here's those results. And he's showing something else. He's saying, here is the cross product, all of this. And we're going to look at something very interesting now. We're going to take the dot product of the cross product dotted with A. Okay? Now, we're just going to watch his math fold out here. And he's seeing how, oh, look at this. These, well, let's see, what is he doing? Oh, we'll keep going. There we go. He's showing how these are grouped similarly. So I got to see myself. Okay, yeah. So this is these are just each of these rows, because that's how you do the dot product. This element, this is all one element times this element. So that's all these are, but what's he saying about it next? He's saying, he's grouping like terms. Well, he's getting ready to do something. Now he's saying, oh, wait, I think I might have missed something. Yes. Okay. Let me take some time to look here. A1, A2, B3. A1, A2, B3. You see that? Those are going to cancel. Now, let's look at the next positive term, A2, A3, B1. Well, look at here. If we change the order, A2, A3, B1, so those cancel out. Now we got this last positive one, A3, A1, B2. A3, A1, B2. Those cancel out. Well, what does that mean? It means that this is perpendicular, it's normal to A. And what happens to the dot product when the two vectors are 90 degrees apart? It's 0, because, like I was saying before, cosine of 0 is 1, but cosine of 90 degrees is 0. And you remember, let's go over here, cosine of theta, when it's 90 degrees, when they're perfectly 90 degrees from each other, this dot product is 0. So that's all he's showing. And then he says, well, wait, that's really good to know. That's very insightful to see that the cross product dotted with one of the original vectors that we used in the cross product is 0. Okay, well, he said, well, what about for B? Let's just make double sure. So he does that same thing again, but this time he groups them a little little more carefully, and he shows that, oh, look, I've got a positive B1, A2, B3, and that cancels down here because this is all one equation because we've got to get a scalar value. And then he looks at here, A2, A3, B1, A2, excuse me, B2, A3. So B2, A3, B1. Oh, there we go. Now we've got these two canceled and these two canceled. What about the last one? I've got B3, A1, B2. Well, there's only two terms left now. So, oh, sure enough, it's right here. So I canceled all of these negative ones with all of these positive ones. And so what does that give us? He's just showing, oh, by the way, he crossed them all out up here. I missed that little point. So he's just crossing them out like we just did. And now they're all crossed out. All these were crossed out up here. And so what he's proven is if you take the cross product and you dot it with each of the original vectors that formed the cross product, you get a value of 0. That means that the cross product vector is normal or perpendicular to both A and B, in our case, X and Y. So that he's trying to show the whole thing here, but I hope y'all see how significant that is. So let's close this real quick and let's go get some more insights. Okay, now we'll just, I'll say restart. By the way, YouTube can be a little funky. You'll get this going, go, excuse me, Saul's player here. If you just do this, it starts, no problem. So I'm gonna pause it. Now, what is he doing here? He's gonna look at the cross product, but point out some different things. So let's see where he's going. He's just saying, and sorry for my there we go. A dot B is the same thing as the magnitude of A times the magnitude of B times cosine theta. And let's remember, if you're new to our group, you can see above in the same notebook how we get the magnitude values of A and B, both mathematically, then in code without NumPy, and then in code with NumPy. But A cross B is a different animal. Look how it's the exact opposite. So the maximum here occurs, and we did this in another lecture, where the two vectors are exactly along the same infinite line, when cosine theta is 1. And then the value of cosine of theta approaches 0 as we approach 90 degrees. And then it starts going back up until we get to 180 degrees. But hang on. No, it starts going negative as we go beyond 90 degrees and go toward 180. But then as we pass 180, it stays, now let me say this right, at 180, it's a -1. So the big points around the circle are 0 degrees, it's 1, 90 degrees, it's 0, 180 degrees, it's -1, 270 degrees, it's 0, and 360 degrees, it's back to 1. So that should make sense. We're looking at the value along the x-axis, so to speak, whereas with sine theta, we're looking at along the y-axis, because this is all kind of this is all perfectly explainable with right triangles that form inside that unit circle as we sweep the angle from 0 all the way around to 360 degrees. But when we do it this way, let's remember, this only gives us the magnitude of the cross product of A and B. So then Saul goes into, I want some insight into this cross product. And so he does something clever. He just says, oh, you know what? I'm just going to take the square of the magnitude of A cross B. Okay, well, how do we do that? Well, he starts going through this operation where he's realizing, well, that's the same, and I hope y'all will agree with this, as saying each of these elements are squared. So if you have a problem with that, let me know, but otherwise, I hope you're all good. And so he's saying, boy, I need to go back and check something real quick. Oh, he's showing this general principle of what I was just worried about y'all believing. And you can prove this to yourself. The magnitude of x, some vector x squared, is the same as squaring each of these components of x. And if you don't believe that, prove it to yourself. It's not hard. All right, so then we're just going through those operations with this, and this gets hairy. It just gets hairy, and sometimes proofs get hairy. It's just a lot of algebra terms to keep track of. But now, once he gets to all of those, he's refactoring over here. See the equal sign? He's just beginning to refactor. So what he's doing in his refactoring is he's factoring out a1 squared this first time, then a2 squared, and then a3 squared. But he's looking at these terms. And what's he seeing? Well, let's see what he gathers. He's just gathering, they're all times a -2. So he just groups that together, and he's looking at the conclusion so far. This is where we've gotten to. Now he's just showing, well, okay, if I do AB cosine theta, what is that? Well, that's the same as A dot B, and so he does that operation. But then he says, well, why don't I square those? I'll square all of these. So he goes through that, and then he starts doing this operation of this vector times itself here. He had a squared here, but he realized he wanted to show it both so he could keep track of things. So you can already see what he's going to do. A1 B1 times A1 B1. Well, that's just A1 B1 squared. And so he's literally just going to say this times this, and this same one times this, and the same one over here times this. And then he's going to go back and do this one times that one, this one times that one, etc., so that all of these get performed. And so it takes a while, even with his fast writing. But what he starts to do to make it more visually helpful is he groups these terms ahead of time. He's wrapping around to the next line, and then he's just putting them in columns and saying what their signs are. But then he finally gets this result over on the right. And let's see. Whoa. Oh, yeah, got to get here. Okay. So he's got this. Well, that's interesting. And then he's got this. He's got this that looks very much like this up here. In fact, it's exactly like it, except he's got a minus here and a plus here. So he does something super cool. He just, well, I'm going to do a legitimate algebraic rule. I'm going to add these two equations together. And so what he sees is all of these cancel out. So we'll probably do a scroll action here now. And then he's saying, well, if I did the same thing with the cross product, oh, forgive me. He's actually saying, and this is one of those jumps in proof. So you may have been asking yourself, why would I have ever thought to do this? Because you were exploring, because you went down a dirt road and you wanted to see where it went. Now, mathematicians in past times, when this was first being discovered, they probably went down many dirt roads that led them someplace. Well, that's interesting, but it's not helping us in a novel way, gain new knowledge. So we keep going, and someone eventually thought, I want to look at A cross B squared and A squared B squared cosine squared theta. And they might have had a reason from other investigations, but They just decided they wanted to check it out. So you can see now he's collecting, let me go over here. He's collecting the terms from up here and the terms from down here in this addition because these two groups already canceled. Oh, my bad. What'd I do? I clicked outside of that. That wasn't helpful. Hopefully it won't start over. Yeah, it did. All right, we'll go back to where we were roughly. There we go. Okay, so but he's already done this operation, and then we were looking at the next operation. And he's showing that how those canceled out. That's where we were. I guess I got ahead of him. And now he's doing this operation where he's just showing, okay, if I have the dot, I'm adding the square of the dot, the square of the cross product to the, and getting, excuse me, I'm getting the cross product, taking its magnitude and squaring it. And then we're taking the magnitude of A and then squaring it, the magnitude of B and squaring it, and squaring cosine theta. Well, this is just that principle we saw here, right here, and saying, oh, I'm going to square each of these terms. And on the cross product, if I'm going to take the square of its magnitude, I'm going to square each of these terms. So that's all that's going on. Oh, so now he's doing the operation. This part is the dot product. This part is the cross product. So let's see where he's going. He's repeating what he had up here. And then what's he going to do? He's going to add it to what he had down here. But notice how he's doing it. I'm sorry. He took this, and when he added them, he got the term that was missing for B in each case. So you see we've got A1 squared times B2 times B3. But down here we had A1 squared times B1. Well, up here, this was missing a B1. So that's all he's doing. He's just adding the B1 here, the B2 to this group, because it was missing right here, and then the B3 to this group. And he's getting those from down here when he added these two equations. So these, again, for the third time, canceled out, maybe the fifth time. And these were just adding the remainders. And it comes out, we see it this way, and then we realize, well, wait a minute, that's just this. And he's absolutely right. So it's all these B's squared and all these A's squared. Well, where's that going? So again, how do you get this? Because remember, this was the dot product squared, and the one above was the cross product, get its magnitude and square it. So that's why he wrote these, because that he was adding those two equations. I should have made that clear. I think I actually took y'all down a dirt road the way I explained that. But now he's just saying, wait a minute, let's look at what's going on here. If I take A cross B squared, and he's just rewriting the above, and he's realizing, let me go through here. Okay. He got this, and he just rewrote it over here. Let me make sure I know what he's doing. E squared, A squared. Trying to remember how he got that. Forgive me, I've had a memory lapse. Let's go to this point. Now, can y'all hear this? Let me know in the chat if y'all can hear this. Let me know in the chat if you can hear this. Okay, right. he's just showing from the principle we saw above. Okay, I'll explain it. Y'all can't hear this, but right here, this part for the b1 squared, b2 squared, b3 squared, that is just the magnitude of b squared. And the same thing for a, it's magnitude of a squared. But he's just showing that's what's going on. But we started with this up here to get to this point. And so he's just rewriting all this again. He's got, he has to rewrite it. He was trying to copy and paste his drawing. So he's just rewriting this equation down here. But from all of this work of adding these two, like we did above, we came up with this, and it's really just this right here. Now he's going to subtract this guy from both sides. So let's just do the simple algebra in our heads. It's this. That's going to equal this minus this. That's how he got there. So I'll jump ahead. And so that's all he's doing. He moved it over. If you want, change the sign, however you do your algebra in your head. So this, you can see these, he factored these two operations out, and it's that times 1 minus cosine squared theta. But if you look at the equation for a unit circle, that's the same, this thing, as you see him doing, is the same as sine squared theta. Watch what he does here at the end. Now we're going to just take the square root of both sides. And it is exciting, as he's saying. It's just A cross B. It's equal to what we said before. So what he did, by doing what he did, is prove why this works with things we already know about. So he went from the cross product and the dot product, another way to do the dot product, he squared them both. And then he gets to this really cool principle of, oh, the cross product, the magnitude of the cross product is just this, like we said, before when we were over here. There it is, right here, the magnitude of the cross product. But he's proving it. Now, if you've ever been one of those students that said in your mind, or you heard your fellow students say, I don't want to see the proof, just give me the equation so I can use it. Well, that's actually you, unknowns to you, begging to not have better insights. And when you continue to look at different problems in life using this stuff, those extra insights are what are the things that will bail you out. All right. So that was the end of that lecture, where, again, he's just going from, I'm going to take the dot product operation and square it, and I'm going to take the cross product operation and square it. And if I were a mathematician when this was first happening, I know exactly why I would be thinking to try this, because this, I found out already, hopefully, that this was normal to, well, this has no direction, so I can't say what I was going to say. Oh, no, sorry. That this might be relatable to the unit circle, which is what he does right here. Sine squared theta plus cosine squared theta always equals 1 for all thetas. And so he did the relation here. By the way, this is like saying, if we go on ahead and say sine squared theta times 1 and cosine squared theta times 1, and it equals 1, this is that unit circle where 1 is always the hypotenuse of a right triangle you're drawing inside a unit circle. And so the hypotenuse of that right triangle is always 1. And these will give you the horizontal leg and the vertical leg. And so squaring them is just saying, well, this is 1 squared. We could write that 1 squared and it'd still be the same. But it's the way to get the hypotenuse magnitude. And that's why the unit circle is so beautiful. We can let that right triangle be swept around inside it, but where the hypotenuse is always the radius as it sweeps around the circle. as we get this cool proof here. Now, I know we're just a little past 9, but we usually go past the hour. Let's do dot and cross product comparison intuition. And we'll do this in the same way. I'll explain through it because, again, if you join late, Thom got sick and he didn't get through all the visualizations he wanted to do. So now he's just getting some intuition about this A dot B. That's the dot product of A and B, and showing that it equals that. And so he's drawing the A and B out in space, and just some general form of it. And he's showing that, oh, I can get cosine theta from A dot B, which is a scalar value, and the magnitude of A and times the magnitude of B in the denominator. And then, oh, well, what if I actually want theta? Because sometimes we actually want to find out the angle. I just have to take the arc cosine of this stuff. So if I take the arc cosine of both sides, the arc cosine of the cosine of theta is just theta. And the arc cosine of this stuff is what we've written here. And so he's showing that's the same as cosine inverse. Now he's going to look at the cross product magnitude, and he's rewriting that. So we've already been through that. Now he's looking at the intuition for, hang on, let me watch. Forgot what he's doing here, but we'll get there. Oh, he's remembering things about a right triangle. So he's going to look at the projection of A, so we want a right triangle here. So we take a sliding line that's, but it's exactly perpendicular to B. And we move it along and make it long enough so that when I project perpendicularly from B up to A, I get a right triangle. And this is the hypotenuse, and this is the horizontal, and that new vertical line is the vertical leg. So there he draws. I should have clicked ahead instead of describing all that. So this is the adjacent, and this is the hypotenuse, and this is the opposite. Oh, whoa, Thom. Well, in case you forgot or never learned it, this is the side of the right triangle that's adjacent to the angle, the defined angle. There's an angle up here too, but no, right now we're looking, if there's a leg, if we're defining the hypotenuse, where this is along one direction, etc., this is adjacent to the angle. And so I can get the cosine of theta is equal to that adjacent side to the angle over the hypotenuse of this right triangle formed this way. So he's just giving more intuition here. And then as we, sorry, cosine. This is some way it's a mnemonic to help you remember sine, cosine, theta. But cosine theta is so, ka, toa. So this was adjacent, cosine of adjacent over hypotenuse. That's his little mnemonic trick, memory trick. So we've got adjacent over hypotenuse. Well, now that we have that defined in terms of these vectors in this picture, we just bring this A over, according to algebra, and we say, oh, I can define the adjacent. And then the A dot B is, it's the same operation, but now it's not projecting, here we'll go more. I just want to show you all more on his screen. Let's see what he's doing here. Dot, here we go. Oh, guess what? Caleb wants to say hi. Can you say hi? Come here. Say hi. Caleb wants out. We're not going to be able to continue unless I let him out. Let's go. All right. No, you'll be in that. You know I'm here. You can't do that. Can't have it. Sorry. dot is a product of the lengths, but also of the cosine of vectors that are the same direction. So that's why we look at these projections. The cosine theta is making cosine theta times A is the projection of it onto B. And now, because it's projected onto B, we can just take the product of A cosine theta, A's magnitude times cosine theta times B's magnitude. That's what he's showing you, because we already knew this. If they were on the same line, that was going to be the max. And so now it's just that projection times B gives us the dot product, or the dot product. Now, what we already said, A dot B is equal to 0 when A and B are perpendicular to each other. And I think he will, well, he just shows them perpendicular, but he didn't write the little right angle symbol, but that's okay. Now he's showing this length here. And that would be, this is opposite to the angle, and it's over the hypotenuse, or A. So he's going to develop that. And this is the intuition for the cross product. And he's just going to show that, oh, A times sine theta equals the opposite length right here. And so if I put that back into this equation, there is the A sine theta part and B. So these two are exactly the same. He's just bringing some more intuition into all of this. And then now he's finally showing you, the point where there's 0 is when they're right angles to each other. And at that point, it's just A, B. Well, why? Because sine theta at 90 degrees would be 1. So might as well drop it for that special case. Okay. And we're almost through. We'll be done a little early today. Again, I hope some of you will say, me. I'm gonna do these proofs in LaTeX, and then I'm gonna write some Python code and some Matplotlib illustrations to show this. That would be awesome. But I'll be doing it too, so we can compare methods. And I bet y'all's will be great, by the way. So A cross B, when they're exactly in line with each other, like right here, theta equals 0, well, the cross product's 0. But when it's the dot product, they're a maximum. And that's why he drops the cosine theta right here, because they're at 0 degrees. Whereas, again, when they're at 90 degrees, it's the flip. Now, more intuition. If you remember back to getting the area of a parallelogram, well, he's doing just what I said. He's taking a copy of B and sliding it up here, keeping it parallel to B, taking a copy of A and sliding it over here to keep it parallel to A. And then that forms this parallelogram. But what is the cross product? Yeah. What is the magnitude of the cross product? Well, it literally is just the area of that parallelogram. And so if we define it as a vector, it'll also have direction, again, perpendicular to this plane we formed with A and B. And you might have said, oh, Tom, we could have gotten that third point with A plus B. Yeah, you sure could have. Okay, Emmanuel. All the time. No, it's a different link, Emmanuel. And that will start about 50 minutes from now, and we'll watch from you. But use the Linktree link or send Ugor a message, and we'll make sure you know how to get to integrated mentoring. Okay. Let's see where he ends up. Yeah, so he was just talking there at the end. Oh, no worries, Emmanuel. Glad you could. We're about to wrap up, so you're good. So this is great. What we gained intuition is, as we go from 0 to 90, well, at 0 degrees, the dot product's the maximum. 0 degrees being the angle between B and A. So when there's no angle between them, the dot product is maximized. But when it gets up to pi over 2 or 90 degrees, that's when the dot products are minimal. But it's flipped, just like sine and cosine are flipped for when we look at the cross product. When the cross product is at 0 degrees, it's 0. The magnitude of that vector is 0. You might even say, well, what's its direction? It's 0. That's going to mess with your head, by the way. We don't know. But you might think, can I find the direction of a 0 vector? You wouldn't need to. But if you just wanted to do for fun, remember how we took limits in calculus, if you've taken calculus. And that'd be a cool way to see what would the vector have been. Now, someone might be saying, oh, Thom, you got to be so careful with the scales of those components. If you're going to look at that and say, yeah, I totally agree. You got to make sure they approach 0 in a very proportional way. But I don't know, that was a little mind experiment, a mind game almost. But yeah, the cross product's a minimal when the dot product is a maximum, and the cross product is a maximum when the dot product is a minimum or 0. So I hope that helped. Though really these last 2 lectures, if I close this is where we went into the cross product, and he did some good proofs there. But these 2 lectures are awesome because they give more intuition about the cross product and the sine of the angle, and then also a comparison of dot and cross products. So next we'll do this vector triple product, and I will catch up, and it'll be fun as usual. All right, guys, any questions? I'll stop sharing so I can take questions. See, Caleb's nudging me. Caleb, any questions? All right, any questions in the chat? All right, guys, I hope this was helpful. Again, Hugo and I are always looking for ways to improve this Machine Learning Foundation's overall recurring meeting. Right now, we're going through Linear Algebra. We're getting help from Saul Khan, but we're taking what he's taught us and putting it into Python so we can calculate, have functions in Python with what he's shown us, visualize it in Python, and I might start adding some other visualizations with Manum. We know we're going to use Visual Python. In fact, that's what I'll also do. I'm going to use Visual Python to visualize dot and cross product magnitudes as the angles change. And that'll be very fun. And we can even do it with a graph. But visualization's our friend and the friends of those we teach. But I actually like to teach the way I'm also doing the visualizations. But we want to do the visualizations and the code next week. And then if we get through those fast enough, we'll move on to these lectures. And this is going to get more fun than any of us deserve to have. Matrices for solving systems of equation. And I tell you, that's going to be some fun coding. All right. I will ask y'all to sign off when you want, but please ask questions in the chat. Ask me or Hugo on LinkedIn. Ask me or Hugo, or me and Hugo on one of those, or in our Slack work group. And which one would you use for that? Just tech chat's probably best. I guess, Hugo, we could make you can use Pipeline Class Chat. Maybe we should have a special chat group in our Slack work group a special chat channel in our Slack work group for this Machine Learning Foundations. But okay, so y'all sign off, and Hugo and I are going to talk a bit, but stay on if you want to ask a question. Y'all take care, and I hope I see all of you at mentoring. I'll stop the recording too.